So how are we going to write this in a compact way? The alphas are the coefficients of the desired characteristic equation, and the a's are the coefficients of the open loop characteristic equation. So this is pretty straightforward. So I could write a vector that looks like this: alpha 1 minus a1, alpha 2 minus a2, all the way to alpha n minus an, right? So I could write a matrix like this. All right, so if I write these equations in a more compact form, I would get something like this. Alpha minus a is equal to, I'm just trying to write these equations in a more compact form, k times, now here's an interesting thing. Look what you are having here. You are having ab, a square b, ab, b, a to the power n. Does this remind you of something where you have something like b, an ab, a square b? It's called the controllability matrix. So you could actually write here the controllability matrix of a, b, okay, times a script a, where script a is a matrix that looks like this. 1, a1, a2, an minus 1, 0, 0, 0, 1, a1, an minus 2, 0, 1, a1 minus 3, 0, 0, 0, 0, 0, 1, 1. Works like this. You will see, just wait. So, my claim is that if you multiply this with the controllability matrix and with k, you will get these numbers. Okay? Just look at it. Script A, I'm writing it this way. There's a 1, 1 all in the diagonal. Zeros in the lower triangle. And in the upper triangle, you have a1, a2, blah, blah, a n x minus 1. And then you have a1, n minus 1, a1, n, and so on and so forth. Okay? You multiply A with the controllability matrix and multiply it with K. At each row, you will get these ones, KB, this one, and so on and so forth. It is nothing but rewriting these equations. Okay? Nothing but rewriting these equations here. It's just a trick, a linear algebra trick that we do. Write this, the controllability matrix, and then multiply it with script A, and you will get that thing over there. Okay? Where the controllability matrix is simply B. Sorry. This is not a big A, okay? This is supposed to be a big C. Is equal to a big C, the pair of AB, the script, the controllability matrix of AB is simply B, AB, A square B, all the way to A to the power n times B. N minus 1, I'm sorry. Minus 1 times B. Okay? So you multiply this matrix with this, multiply it with K, you obtain this one. And you can see it on the first item is actually quite straightforward. Zeros and ones, multiply it with the controllability matrix, you get 1, multiply B with K, here it is, K times B. The first one, right? Ones, zeros, multiply this, you get B, B times K is the first line. It's the first row, okay? Straightforward. The second line, you will have an A1 and a 1, which means B times A1 times K, and then 1 times AB times K, and here it is, KAB, A1, KB. Okay, that's the second row. So it's that. Understood? So what's the significance of this A script? Nothing really. It is just a matrix that looks like this, which is quite straightforward to obtain because you have zeros, you have ones, and these ones are the coefficients of the open loop characteristic equation. So it's actually quite simple. If you had a system like this, A minus AX plus BU, this is the open loop. All you need to do is write the eigenvalue equation for A, obtain the coefficients of that open loop of the eigenvalue equation, basically of the characteristic equation of the A matrix. Those coefficients, you just write them into this matrix with ones over here, and you put it like this. Write the controllability matrix. Write down the coefficients that you want. Subtract it from this, from the characteristic equation of this one, and you can obtain K from here. Now, of course, K is now hidden here. We have to obtain K from this, and if you obtain K, you end up with the Bass-Gura formulation finally. From here, K now will be equal to alpha minus A over minus 1, script A over minus 1, and minus 1 of the controllability matrix. The inverse of the controllability matrix, inverse of A, and alpha minus A. And that is your formulation for K. You have to take two inverses. One is this one, the A, and one is this one for the controllability matrix. Question is, of course, do these inversions always exist? For script A, I can say it always exists. It's a upper triangular matrix. You have ones in the row. I know this will exist, the inverse. How about the controllability matrix? Will it always exist, the inverse? Or when doesn't it exist? It would exist when? It will not exist when the system is not controllable, which means the inverse will exist if this matrix is full rank. Okay? When is it full rank? When it's controllable. When the system is not controllable, inverse will not exist, and therefore there is no solution for K. So this inversion, the full rank condition for controllability, shows up here as well in the formulation. If the system is not controllable, there's no unique solution for K. Okay? And this is what we did a few weeks ago, where we said, if the system controllable, right? We looked at it. Is the system controllable? If the system is not controllable, which means there is no solution to go to that point, then I cannot find a K, a feedback gain K, that will take me everywhere. Right? So this shows up in this formulation in a mathematical form, saying that controllability matrix must be full rank for K to uniquely exist. Otherwise, this is not invertible, and therefore there's no solution, unique solution for K. Okay? Good. Wonderful. So this is your Bass-Gura formulation. Now, why is this good? Why is this formulation so nice? It's so nice because you can write it in a computer program, for instance, right? There is no restriction on anything here. I mean, the example we did last week, you had to do some algebraic manipulations by hand. But here, the size of the A matrix can be any size. It can be 5, 10, 100, whatever, right? And it's quite straightforward to write this one. You find the coefficients of the characteristic equation. It's quite straightforward to find the controllability matrix. It's quite straightforward to find the inverse of these matrices in the computer. And you can multiply these things and boom, you have your K matrix written in a little code that you have written. Okay? So it's a systematic way of doing this. Any questions? As I said, the proof here, I mean, I realize that I jumped here a little bit, but you know, I'm giving this to you so that you have some sort of feeling of where these things are coming from. And if you're really interested, you can go into books and look through these steps and go to linear algebra and all this. But what's more important is that how we set up the problem, how it tries to really match these two characteristic equations. And then that there is a solution to this. And the solution actually shows up like this with the controllability matrix requirement to be invertible, which means it needs to be full rank. Okay? Any questions? All right. So let me do an example. Actually, let's do the example that we did last time by hand, remember? And see if we get the same solution. Example 1, redo the previous example. In fact, the previous example was something like that. X dot is equal to x plus 0, 4, u. It was a single input system, right? The Bass-Gura that we have obtained is for a single input system. The desired characteristic equation, we found it to be was found to be like this. .35 S plus 625. This was the desired characteristic equation. And the open loop, we can find the open loop quite straightforward, right? We just take determinant of this one, minus 3 minus lambda 8, 0 minus lambda is equal to 0. And what you obtain from this is alpha square plus 3 lambda minus 0 is equal to 0. Right? This is your eigenvalue problem, really. And you set this equal to 0. In that case, the closed loop characteristic equation would be, now open loop, I'm sorry. Okay, AS is equal to this one here, S squared plus 3S minus 0 is equal to 0. In which case, A1 is equal to 3 and A2 is equal to 0, right? 0 and 3. And here, alpha 1 is equal to 35.35 and alpha 2 is equal to 625. Okay? You see how I'm setting up the problem. the desired one is usually something that is given to you as a designer, or you have to obtain it somehow. What do we want a closed loop to look like? Right? That's the whole goal of what we do as controllers. We have the open loop characteristic, we have the open loop system. We are adding a feedback gain K so that the closed loop looks different. So how do you want it to look different? That's up to you. So you need to have some sort of a desired characteristic equation or something. Where do you want to put the poles, right? So looks like that, and this is that. Any questions so far? Good. So in order to set this problem up, let's find the characters, controllability matrix, and that is equal to B times AB. So B is here, 0, 4, and AB you multiply that, it should be 32 and 0. Right? So, can you take the inverse of this? Do you know how to take the inverse of a second order, of a matrix of a second order? Right? You know that, right? You need to find the determinant, right? Maybe 1 minus the determinant and all this. Want me to write it down in the corner? This is something that you should know, really. Let me write it down. If you had a matrix that looks like this, A, B, C, D, the inverse will be 1 divided by the determinant of A times D, B, C, A minus. I mean, this is how I remember it. It's 1 over determinant A. Oh, sorry. And then you switch these two, this one, and you put minuses on these ones. Right? Switch A and D, C and B, and put minuses on this diagonal. This is what you should know this. I think for the exam at least you need to know how to take the inverse of a second order. I'm not expecting you to take the inverse of a third order or a fourth order, right? But this one you should at least know. Right? This is simple stuff. All right, so let's do it for this one. The determinant of that controllability matrix, I think I found it. It's actually quite straightforward. Yeah, it's 128. This one minus this, right? It's 128. So it is 1 divided by 128 times 0, 0, 32, 4, and you put minuses. Minus 1 over what?
The determinant is 1.
Oh, it's a minus. Sorry. Yeah. Okay. And that will be equal to. What did I do wrong? Oh, whoa. See, I don't I don't remember this quickly anymore. These ones you don't these ones you don't switch. Yeah, now it's okay. You switch the A and B. These ones you don't switch. You just put minuses there. See, I forgot it too. Maybe I should give this in the exam, just as a disclaimer what to do. I don't like these. I don't like memorizing these things really. I mean, there's so much information in the world right now that you need to use your brain for the things that are really important. For the things that are not, you probably have to don't waste time with it. I always thought this was, but you can make a mistake. Yeah. Okay. All right. So what do I have? I have this 0, 0.25, 0.03125, and a 0. Okay. That's the inverse of the controllability matrix. Okay, so let's write script A. 1, 1, 0. And the first one will be A1, of course, right? Because it should be of order 2, because we have a 2-order system. So 1, 1, A1, right? So it is 1. A1 is where? It's 3, 0, 1. Take the inverse. 1 minus 3, 0, 1. See, this is not necessarily very straightforward. I think this would be really good if you would write this into a computer code. Now we need to find the vector alpha minus A1. So alpha minus A, is equal to alpha 1 minus A1, alpha 2 minus A2. So it's here. Alpha 1 minus A1 is 32.35. And that minus that is 625. So, and I'm sorry, this has to be this plus. Please put a transpose over here. This is a row vector. Okay. Yes, it was a vector like this, but it has to be a row vector. Is that right? Just one second. Let me just think about it. 1 second. That's not even true. Just wait. This doesn't even look right. Yeah, that's right. That's true. Please put a transpose over here, okay? This is K1 and K2. So can you calculate this? Do you have a calculator? What do you get? This has to be a transpose. Here. Basically, it's a row vector, okay? This has to be a row vector. Let me put it in my notes too. It's a mistake here. Oh, actually, I have it in my notes. This is a transpose. I just forget to write. Okay. Did you find it? The first one? Okay. 16.5 or 05?
16.5.
Okay.
8.01.
Anyone else found the same? Is this true? Yes? Is this the same result we found previously? It's the same, right? Okay. So the formula works, right? Good. So this is your result, and the formula works. Now, how do you like this? Do you like it? Is that good? The nice thing about this is that it's systematic. As I said, you could write a computer code for this. And it will always give you good results regardless of how big the system is. Because sometimes the system can be very big, it will be very tedious to find the problem. So, any questions? All right, so this is one way. The Bass-Gura formulation is one way of doing this. Another popular formulation to do this is the so-called Ackermann's formula. For this, I will not try to give you the proof, okay? Ackermann's formula. I will not try to give you the proof. Let me just write you what it looks like at the end. It's K is equal to 0, 0, 0, all the way 1 times the inverse of the controllability matrix times alpha A. And alpha A, where the function alpha S is the desired characteristic equation. A lot of people find this to be a little simpler. As I said, MATLAB Simulink is using this. Well, it's up to you. You make the decision. I'm not going to give a proof for this like I did for the Bass-Gura. It just becomes too much for this course at least. But let me solve, but this is a very simple formula. This is again the controllability matrix. It also requires the inverse of the controllability matrix. It requires alpha A, this is the matrix A, and some vector, basically this one, is equal to K. Now, let's do this example using the Ackermann's formula, and you decide which one you want to use in future, okay? Example. Again, previous example. Example. So A is equal to this, minus 3, 8, 0, 0. B is equal to 0, 4. Okay? And alpha S was what? Now it's here. Alpha S was equal to S squared plus 35.35 S plus 625. Okay? This was the desired characteristic equation. This was a desired characteristic equation. Basically, we say we have an open loop system that looks like this. Again, just to remind you, this is a linear system. It's a linear system that was linearized around an equilibrium point, right? So it's only valid around that equilibrium point. It's a linear system. It's a second order linear system. We are trying to design still a full state feedback controller. Full state feedback. And our job is to design a feedback gain K such that this desired characteristic equation is met. All right, just to remind you. So, and the feedback gain K can be found using Ackermann's formula, which is this one. So, first, the controllability, the inverse of the controllability matrix, we already know. We found this in the previous example to be 0, 0.25, 0.03125, 0. So what we need to find is alpha A. Now this is interesting, right? Because S is really this is the characteristic equation. S is a variable, but A is a matrix. So how do we do it? Here's how we do it. S square now means A square, which means this. Minus 3800 times minus 3800. That's A square. You see? A square. This one. Plus 35.35 times minus 3800. Right? Plus 625. Now 625, you can't really write it like this, 625, because this is now a vector, a matrix, and this is a scalar. So you need to do this. Multiply it with an identity matrix so that this actually becomes consistent. Okay? 625, identity, A matrix here, and this is the identity matrix. Is that okay? So, if you find this, you will get a matrix multiplied with the inverse of the characteristic with the inverted control matrix, multiplied with this vector, and you get K. Let's do that. Okay, therefore, will be. Now this is a second order system, therefore you have 0 and 1. I mean, the numbers over here, this should be totally n, whereas the zeros are basically n minus 1. You have n minus 1 of those zeros, and the total, of course, then has a size n, otherwise it would be inconsistent, right? So therefore, this is a second order system. It should be 0 and 1. In total, there are two numbers here. Okay, inverse of this. Times this. So what do you get? Yeah, well, you should get the same stuff. K1 and K2. Is that good? Want to try this? Not really. Okay. You try it at home, or you just have to believe me. Okay. So which one do you like better, the Ackermann or the other one? Well, it's your choice. Both of them work very well. As I said, MATLAB and Simulink is using Ackermann's formula to calculate these feedback gains. Okay? Any questions? No. All right. So one thing that we did this time was simply, so far, I mean, including in our previous lecture, we always looked at single input cases, right? We looked at single input cases, and we could uniquely find a feedback gain K. All right? So what happens if you don't have a single input case? What if you have more inputs? Okay? So any questions here? I'm going to erase this now. This is kind of the end of the single input case. Okay. So multi-input case. Okay? So if it's not a single input. I always found this the simplest if we look at do it this way. Okay. I always found it the best to show you what happens if you have a multi-input case by giving you an example. So in the previous example was actually quite simple. I had u, x dot is equal to ax plus bu. The output was x. We took x. In fact, x is equal to x1 and x2. We multiply this with k1 and k2, and we get some variable v added to this, and this is r, and this is r minus 1. So if you want to write this block diagram in a more detailed way, you would get x dot is equal to ax plus bu, right? You would take x1 multiplied with k1 subtracted here, this is r, and you will get another one. This would be x2, multiply it with k2, and also subtract it over here. Right? And we found in the previous example, we found k1 to be equal to 16.5 and k2 to be 809, right? So basically what you would do is you would measure x1 and x2 in your system, right? And multiply it every time with 16.5. And this one you would multiply with 809, right? And then subtract it from the input that the pilot is giving you. Subtract it from that, that would be u, and so on and so forth. So this is your feedback gain. And how do you do this? I explained it to you, I think, a week ago or 2 weeks ago. Basically, if this was an airplane, at each instant you would measure these variables, multiply it, and send it back to the controls. And how many times would you do this? You would do it about 60 times a second, 70 times, sometimes 100 times a second. You would measure, multiply, take it back. Measure, multiply, take it back. right? You would do this all the time. And remember, this is still a linear system. Basically, it is everything is offsetted from the equilibrium point, which is 0, 0. Okay? So you might think if x1 is, for example, the velocity, how would you multiply 60 times a second the velocity with 16.5 and send it over here? But that's not really true. If this was velocity, this would be delta velocity. It would be everything offsetted from the trim point. If you don't remember that, go back to the videos of flight mechanics, which are in YouTube, right? Look at small disturbance theory, look at linear systems. Linear systems are always offsetted from their trim point. So therefore, the equilibrium point for a linear system is always 0, 0. In other words, for instance, if x1, if you are looking at a system where u is the velocity, and let's say q is the angular rate, if you would write a linear system for this, it would look like this. Del u dot is equal to, del u dot and del q would be equal to A matrix times del u times q. So x1 would be del u and q. It would not be u itself. It would be the delta from the equilibrium point, right? So therefore, x1 and x2 will never be very large numbers. It will be offsets from the trim points, okay? So if you're at the trim point, the output x1 and x2 will be equal to 0. Because at the trim point, delta u is equal to 0 and delta q is equal to 0 at the trim point, right? So at the trim point, the feedback would be 0. You're sitting at the trim point, right? But if you're not at the trim point, it will be the offset from the trim point, and you would be multiplying that offset with some numbers so that it will come back. If it's back at 0, the system, the output will be equal to 0, okay? Because if you look at this equal to 0 has really one solution, which is the trim point for the linear system. The linear system has really one trim point. This equal to 0 is the trim point, right? And this has one solution where this is equal to 0. Del u is equal to 0, q is equal to 0. That is the only that is the only equilibrium point of the linear system. The nonlinear system, the equilibrium point might be, let's say, 900 knots, or maybe it's too much, 900 kilometers per hour flight of a passenger airplane, right? And that is your equilibrium point. But if you write the linear system, it will be a delta u, which is the delta from that equilibrium point. I think I will give you one more homework. But in the homework that you did, you had a linear system of an airplane, right? Is that right? Okay. So the linear system was actually linearized around the equilibrium point, and it had delta u in it, right? It is the offset from the equilibrium point. So when you're feeding back, when I say you feed back the state, I don't mean you're feeding back 900 kilometers per hour multiplied with 8, and you have 800 and send it to the controls. It is the delta u that is from that equilibrium point, okay? So the aircraft might be flying at 900 kilometers per hour, and if you're away from 900 kilometers per hour, the trim point, let's say you're at 902 kilometers per hour, so you're only 2 kilometers per hour away from that equilibrium point, so the feedback would be that delta 2 kilometers per hour. It would not be 902, okay? Because the state is equal to delta u dot. The state is not equal to u dot itself. Although I keep saying x dots and x1, x2, those are all linear states, offsets from the equilibrium point, or wherever it is linearized from. Does that make sense? See, this is a point. It's quite simple, and it's quite straightforward. But what I see in students is that they keep forgetting this point. You know, even at engineers, every now and then I see people feeding back 900 kilometers per hour. It's not. It's delta u, which means it's the offset from that equilibrium point. Understand that? And so is the controls, by the way. The controls are also offsets from the equilibrium point. So if you have the throttle at 98%, let's say, and that is your equilibrium, everything you're doing here will be the offset to that equilibrium. Okay? So if you get a u that is 1%, 2%, it will be always around this 98% of equilibrium point throttle setting. That makes sense? Okay, let me give a break, and please think about this point, and if you have questions, ask me, because this is a very fundamental point. And as I said, I keep seeing people, even after graduation, making that same mistake over and over again, and not really understanding that the linear system that we are doing here is still around an equilibrium point, and every variable in that linear system is an offset from that equilibrium point. Understand? All right, so let's give a break.